Hi everybody, I'm Brannon. Today I'll be explaining to you how to solve problem number 5 from midterm number 1. This problem gives you two spheres, an inner sphere, conducting sphere, carrying charge Q with radius big R, and an outer insulating sphere with charge density rho with inner radius R, or big R, and outer radius 2 big R. The first part of this problem asks you what is the value of rho such that the net charge of this system is 0. To get this, you have to set up the equation rho times V of the outer sphere, the insulating sphere, plus Q equals 0. Now, to get the volume of the outer sphere, you need to get in terms of volumes that you can find, which is the volume of the inner sphere and the total volume of the spheres together. So there you have VT, volume of the total sphere, minus VI, volume of the inner sphere, plus Q equals 0. Now, from here you can substitute in expressions for the volume of these spheres using the equation for the volume of a sphere, V equals 4/3 pi r cubed. So substituting in these values, and subtracting Q from both sides, you get the expression rho times 4/3 pi 2 big R cubed minus 4/3 pi big R cubed equals negative Q. Now, working this out, you get that 2Q times 4 equals 32. 32 minus 4 equals 28. So multiplying both sides by 3 and dividing both sides by 28 pi big R cubed, you get rho equals negative 3Q over 28 pi big R cubed. This part of the problem also asks you what is the potential difference, delta V, between R equals 0 and R equals big R. The answer to this is trivial because we are talking about a conductor here, and there is no electric field within a conductor, as a property of conductors, so moving from this point, these points will not cause any difference in electric potential, so delta V equals 0. The second part of this problem asks you to find the magnitude of the electric field for all regions in the problem. R less than big R greater than big R, less than 2 big R, and R greater than 2 big R. Because this problem has spherical symmetry, we can use Gauss's law to solve it, and we can avoid using Coulomb's law because nobody likes it. So, the form of Gauss's law is, of course, the line integral over surface integral over a closed surface of E dot dA equals Q enclosed over epsilon naught. We're only going to need to use this in the second part, though, because the first part is talking about the inside of a conductor, for which there's no electric field, so E equals 0. Now, in the second part, we need to, gotta grab a notebook here, we need to work out E in here, so we have to substitute in all of the values we know. So, the closed surface integral of E dot dA is equal to, our Q enclosed is going to be Q, which is the charge of the inner sphere, plus whatever we have enclosed as the outer sphere, which is going to be the volume enclosed times our charge density. So that value is going to be rho times 4/3 pi r, small r, which is our variable r, cubed, minus big R cubed, and all of this will be over epsilon naught. So, working from here, we need to we can get rid of this integral because at all points the dot product between E and dA is going to be the same magnitude as multiplying E times A. So we can get rid of the integral, get rid of the dot product, so it becomes E times A, which can be expressed as 4 pi r squared, because we're dealing with the surface area of a sphere, equals all of this that we had on the other side. Rho times 4/3 pi radius cubed minus big R cubed all over epsilon naught. Dividing both sides by the area and substituting our value for rho, we get the expression E equals Q plus minus 3q over 28 pi big R cubed pi 4/3 little r cubed minus big R cubed, all of this over 4 pi r squared epsilon naught. And this is all a very complicated expression, but the rest of the math in this problem is just simplifying fractions, and I'm sure you all can do that. So working from there, the final answer becomes E equals 2q over 7 pi r squared epsilon naught 1 minus little r cubed over 8 big R cubed. That's your final answer. And then for r is greater than 2r, since we have decided that the net charge of the system has to be 0 in the first part of this problem, the charge enclosed when your Gaussian surface is larger than the sphere will be 0, so by Gauss's law, the electric field will also be 0.